This video is going to be less of a tutorial and more of an explanation about the various data that gets lost as you convert it to be used in the viewer. So to start with, if you look at a DICOM image, it has 12 available bits per pixel, which gives it a range of 4096 values, whereas we are going to be converting to 8 bits per pixel, which only stores 256 values. So there's an obvious loss in quality here. To limit this a little, it's recommended that you first window your image to the bottom 2000 pixels before converting it to the 8-bit format. So the reason we can get away with windowing away everything but the bottom 2000 pixels is because in the human body, most of our values are in that range. This means that rather than only being able to retain a 16th of our data, we're able to retain an 1/8. So what happens when we window our image to only show the bottom 2000 pixels is we stretch out the values to where they take up the entire grayscale. And then later in the viewer, we might want to window in on certain regions further, so you can see the hump in values here. So if we restrict our window to only occur around the hump, you can see we're starting to get what might look like an abdominal window. So if you're following along, the first thing you would do when checking out the values lost in your images would be to download the scripts which convert DICOMs into PNGs. Extract your scripts in with the DICOM files, open a terminal in the window, and the first thing we need to do is convert the DICOMs to an ASCII format. So use DCM to ASCII. I'm in Linux, so I'll be using the .sh file. If you're in Windows, you'll use the .py file. If you're using Python for this, you'll need the PyDICOM module as well as NumPy. Now that we've generated the ASCII files, look at the information printed on the console for the slope and intercept. Open your ASCII to PNG script. A slope of 1 and an intercept of -1024 is very common. Here you can change the window. We're going to go from 0 to 2000. This is what I've always called the zeroed window. Once the ASCII to PNG8 script is finished, it'll tell you various information about how many values actually made it into your window and how many didn't. So I'm going to make a copy of my PNG8 folder and save it as PNG8 2000 zeroed. And now, instead of doing a zeroed window, let's do the full window from 0 to 4095. You'll notice these images are coming out a little bit darker, and that's because all of the values in the human body, for the most part, are in the lower range. Again, when the script finishes, it'll tell you how many values made it into your window, and you'll notice this time there were no values above our window. So you would make this full image if you had a lot of values that were more dense than what was typically found in the human body, but that's rare. And lastly, we're going to simulate a 16-bit format, which shouldn't lose any information from the DICOM. So open up ASCII to PNG16 and set your slope and intercept if they're different. It's worth mentioning that DICOMs normally don't stop at air. They go 24 values below air, so our intercept is going to turn all of those values into 0. If you want to keep those values, then you should set your intercept to be -1000 instead. Okay, now these simulated 16-bit images look a little different. They're kind of grainy and green. They won't actually be usable until they're recombined in the viewer itself. So go through each of your newly created image sets and tile them to be used with the viewer. Now make a copy of your server files and put in your new images. Because my old files were also PNGs, and I don't intend on distributing these on the internet, I don't have to change my assets.txt file with the new size information. I will still have to change slidedim.txt with the tile coordinates. Now start your server. I replaced files 5, 6, and 7 because pressing the 1 key alternates between these 3 files. Pressing the 2 key will generate shaders for these files, and as I press 1, it'll swap out the appropriate shader for each file as I come to it. Now you'll notice when I go to the 16-bit file, it's dark. This is some sort of bug with ImageMagick whenever it tiles it, but if you open up the image in GIMP and re-export it, it'll look fine. As GIMP exports the image, it might move the saving bar down to the bottom here, so make sure that bar finishes before you actually reload your server, otherwise you'll only get half an image. So let's reload the page and look at our images, and the 16-bit looks fine now. I had mentioned that pressing the 1 key actually changes the shader on a specific file, and you can change these shaders yourself. They're called custom passkey 1 2, and 3. 1 is specifically for image 5, 2 is for image 6, and 3 is for image 7. So I'm going to change these to an abdominal window. And let's take an image of each of the different files and put them in GIMP so we can see how much information was lost. Notice on the 16-bit image, it does actually have some lost information, and this is because our abdominal window is too narrow to actually have enough values from the original DICOM to fill the 256 values in the grayscale. So our window width was 250, so we're missing 5 values. And we can see that the zeroed image is missing a lot of values, and the full image is missing even more. But notice that the images still look relatively similar. And if we look at the image from a DICOM viewer, it is also missing 5 values. As we cycle through the images, you'll notice that even though the number of values they use vary wildly, they all look pretty much the same. So now we're going to go into the different features of each of these windows. The CT image I chose has this strange melted rebar or something going through the guy. I don't know what it is, but it makes a lot of values very high in the spectrum. So we can see if we set our window value high, the anomaly is the only thing that shows. So let's set the online CT viewer's windows equally as high. You'll notice in the zeroed window now, the whole image is black. And this is because we cropped off everything at these really high values. However, the full image still has the anomaly as well as the 16-bit. Finally, let's say you want to make an image that has a window just higher than 2000, but you don't want to go the whole 4095 range. You can still do that. Just set your window in your Python script and output the images. You'll have to calculate your new width and level. So the width is just the high point minus the low point, and then you can get the level from the 0 by adding the low point and half of your width. And because HU has negative 1000 as air, you'll want to subtract 1000 from your level from 0 to get the actual level in HU. So we're going to use the zeroed window generator to create a window for this new image. So first, go to the advanced windowing section on the page and enter the values that you rendered your window at. So our level was 250 and our width was 2500. And then enter the values you want your new window to be. So this will be the values you'd enter in the online CT viewer itself. So we're just going to go with a full zeroed window, so a level of 0 and a width of 2000. And it will give you the new offset units for the viewer. So create your window with these new values. And I'm also going to create a zeroed window for my zeroed image. And as we cycle between the two, you'll notice they look the same. And if I turn off the window, you'll see that the image we just made is a little darker because our wider range pushed the normal values in the human body down a little bit.